So, in this session we are going to discuss about some of the gate problems related to project engineering. So, this is 2011 2 marks problem. A process plant, what it states, a process plant has a life of 7 years. So, n is equal to 7 years and its salvage value is 30% of definitely this installed plant cost. Find the minimum fixed percentage factor, F minimum factor, for what minimum fixed percentage factor will the depreciation amount in the second year D2 by fixed percentage factor second year calculated, this will be calculated by declining balance method. Is equal to the calculated depreciation in the same year by straight line method. So, here let this installed plant cost, let the installed plant cost is C and salvage, that is Vs, is 0.3 C, right. So, the depreciation over the service life is C minus 0.3 C, which is 0.7 C. So, in straight line method it will depreciate by equal amount in each year. The depreciation per year by straight line method is definitely 0.7 C divided by 7, because this is 7 years, so which is 0.1 C. Now, the depreciation in the second year by fixed percentage method. See, we have C in the beginning of year 0. Now, depreciation DA1 will be equal to C into F. So, its asset value is C into 1 minus F. Now, depreciation in the second year is C into 1 minus F into F, right. That is DA2 and this is DA1. So, DA2 is equal to, calculated by declining balance, must be same as that of DA. This is DA2, that is DA2 by straight line method. So, we have C into F into 1 minus F is equal to 0.1 C. So, that is F minus F square equal to 0.1. So, F square minus F plus 0.1 equal to 0. So, it is a quadratic equation. So, F is equal to minus B minus 1 plus minus root over of B square, B square is 1 minus 4 into 0.1 divided by 2. Right. Yeah. So, this is 1 plus minus under root 0.6 divided by 2. So, one answer is 1 plus 0.6 by 2 and another is 1 minus 0.6 by 2. This is the minimum value because my question was solve for this minimum fixed percentage factor. So, this will be my answer. Right. Not the first one, but the second one. So, another problem. This is also 2011 2 marks problem. A continuous fractionator system is being designed. The following cost figures are estimated for reflux ratio equal to 1.4. What is the fixed? What is the cost figures? This is fixed cost including all accessories. And here we have the operating cost. This is in rupees per year, this is in rupees. So, for column, the fixed cost is 6 into 10 to the power 6, then condenser 2 into 10 to the power 6, then reboiler. These are the fixed cost 4 into 10 to the power 6. This is cooling water in condenser 8 into 10 to the power 6, steam in the reboiler 1 into 10 to the power 6. The annualized fixed charges is 15% of the fixed cost. So, what we have to calculate? The total annualized cost. So, total, you can understand it, total annualized cost is equal to fixed cost per year, right. Fixed cost per year this fixed cost is given as rupees and plus fixed charges fixed cost per year we do not have to calculate here. Fixed charges plus this operating cost per year. So, fixed charges is 15% of the fixed cost. So, total fixed cost is 6 plus 4 plus 2 into 10 to the power 6 into 0.15 plus the operating cost 8 into 10 to the power 6 plus 1 into 10 to the power 6. So, this is 12 12 into 1.5 12 into 1.5, that is coming to be 150 into 1.8 into 10 to the power 6 plus 9 into 10 to the power 6. So, it is 10.8 into 10 to the power 6 rupees. That will be the answer. So, total annualized cost will be this. Next, this is 2012 2 marks problem. A batch reactor produces 10 to the power 5 kg of product per year. Product is equal to 10 to the power 5 kg per year. The total batch time in hours hour of the reactor is K into under root PB, where PB is the product per batch. And K is 1 hour per kg, under root kg. So, operating cost of the reactor is 200 per hour. 200 per hour, okay. Annualized fixed charges 340 into PB, where PB is the product per batch in kg. Raw material cost is 2 into 10 to the power 6 in rupees. The optimum size in kg for each batch. So, we have to find out the optimum size for each batch. Now, if the batch produces PB kgs per hour or PB kg per batch, then number of batches N is the total product, number of batches per year is the total product divided by kg per batch, which is 10 to the power 5 divided by PB. Right. So, total operating cost is N, the number of batches, into the number of batches into the batch time. Total batch time is under root of PB into 200 in rupees. Right. Annualized fixed charge is given, raw material cost is also given. So, the total cost T is equal to 10 to the power 5 divided by PB into under root of PB into 200. Right. So, plus this annualized fixed charges 340 into PB plus the raw material cost 2 into 10 to the power 6. So, this gives you 200, so 2 into 10 to the power 7 under root of PB plus 340 PB plus 2 into 10 to the power 6. So, we have to minimize the total cost. So, dt dPB equal to 2 into 10 to the power 7 into half into 1 by PB into, sorry, here this is not under root, this is minus half. So, this will be minus half into 1 divided by PB to the power 3 by 2 plus 340 equal to 0. So, from there we can solve actually for this PB optimum. So, okay. Next, is a problem on this break-even point. What is that? Heat integration is planned in a process plant at an investment of, so capital investment is 2 into 10 to the power 6 rupees for heat integration. This would result in a net energy saving of 20 gigajoule per year. If the nominal rate of interest is 15% and the effective life of plant life is 3 years, then break-even cost of energy. The break-even cost of energy, which is just equal, let it be E. So, what we are doing actually, we are investing this C and we are getting back this net energy saving is 20 into 10 to the power 6, or rather let us say E is in rupees, what we have to adjust rupees per gigajoule. So, 20E, then we have 20E at the end of first year, at the end of second year, and at the end of third year another 20E. Right. So, we have to project it to the present. So, it is a problem of net present worth set to equal to 0. So, and that projection will be facilitated by this interest rate. So, C is equal to 20E divided by 1 plus I plus 20E divided by 1 plus I square plus 20E divided by 1 plus I cube. So, this is 20E by 1 plus I, 1 plus 1 divided by 1 plus I plus 1 plus 1 divided by 1 plus I square. So, what will be the sum? Here the factor is less than 1. So, 1 minus 1 divided by 1 plus I square 1 minus 1 plus I. So, you see it is 20E 1 plus I whole square minus 1 plus I minus 1, denominator is 1 plus I whole square, numerator is 1 plus I, and there is an 1 plus I here. So, this cancels out with this. So, it is 20E into 1.15 square minus 1, this is 0.15 into 1.15 square. And from there, that is the total capital investment, which is 2 into 10 to the power 6. So, we can calculate the cost of E, or that is the power. Okay. This is a problem of 2013, 2 marks problem. The purchase cost of a heat exchanger, that is the procurement cost, is 5 lakh. How many zeros? 3 zeros. 6. 0, 0, 0, 0, 0. In 2006, this area is 20 meters square. What will be the estimated cost in rupees to the nearest integer of a similar heat exchanger? So, A1 is this. So, what will be the procurement cost of this in 2013, where area is 50 meters square? Assume 6/10 power rule, factor rule for scaling, and cost index of 2006 is cost index 2006 is 430.2, cost index in 2013 is 512.6. Now, you see that we have to calculate this first, the cost index or cost of 50 centimeter square area. We are doing it in this way: 50 meter square area heat exchanger in 20 meter square heat exchanger in 2013. So, 5 lakh divided by cost index in 2006, 430.2 is equal to CV 20 meter square divided by cost index in 2013, 502 plus 6. So, you have to solve fast this CV of 20 meter square. Now, CV of 50 meter square divided by CV of 20 meter square is equal to 50 by 20 to the power 0.6, and we will get the CV of 50 meter square in 2013. Right. Okay. 47, this is also 2013 problem. A plant manufactures compressor at a rate of N per day. The daily fixed charges is 20,000 per day, and the variable cost per compressor is 500 plus 0.2 n to the power 1.3. The selling price is 1000 per compressor. The number of compressors to be manufactured to the nearest integer in order to maximize the daily profit. So, profit is, let n compressors are produced per day, then that n we have to determine. So, 1000 n minus cost. So, cost is fixed charges is 20,000 plus 500 plus 0.1 n to the power 1.3 multiplied by n. Right. So, that is my objective function. So, dPdn, as there is single variable, is 1000 here, then 500 will 500 because 500 n minus 0.2 into n to the power 2.3. So, 0.2 into 2.3 into n to the power 1.3 once again. So, from there we can solve for this n optimum, setting it equal to 0. Right. Now, if you want to calculate the break even, this you have to set it equal to 0, and from there by trial you have to calculate n. Okay. This is 2014 problem. Cash flow of $12,000 per year is received at the end of each year for 7 consecutive years. The rate of interest is 9% per year compounded annually. The present worth of such cash flow at time 0 is. So, you see the cash flow is per year received at the end of year. So, this is R1, Rn, right. What will be the present worth? So, present worth is R1 divided by 1 plus I, R2 divided by 1 plus I square plus Rn divided by 1 plus I to the power n, or sorry, here all are same R. So, R divided by 1 plus I, then it is 1, and 1 minus 1 divided by 1 plus I to the power n divided by 1 minus 1 plus I. So, from here this R is known, interest rate is known. So, present worth will be basically equal to $12,000 divided by the interest rate is 9%. So, 1 plus 0.09 into here it will be 1 minus 1 divided by 1.09 to the power 7, 1 minus 1 divided by 1.09. So, from there we can solve for the answer. Next, this is also 2013 problem, 14 problem. The polymer plant with a production capacity of 10,000 tons per year has an overall yield is 70% on mass basis. What is yield here? The kg, the yield is defined as kg of product per kg of raw material. The raw material cost is $50,000 per year, per ton. A process modification is proposed. So, there is a process modification is proposed which increase the overall yield to 75% with an investment of 12.5 crore. So, the 75% yield investment is 12.5 into 10 to the power 7 crore. This is in crores, so 12.5 into 10 to the power 7. In how many years the invested amount will be recovered? Will be recovered with the additional profit. So, you see this initially it is 70%. So, capacity is, so raw material cost before modification is equal to 10 to the power 4 tons per year divided by 0.7 into 50,000 in dollar. So, raw material cost after modification let us say it is R1, a cost is C1, C2 is 10 divided by 0.75 into 50,000, because the yield has increased to 75% and you have invested this. So, payout period, or not the payout period, we should say that here year of recovery, say this is C2, so investment is 12.5 into 10 to the power 7. Definitely the raw material they will be saving, so C2 will be lower than C1, so C1 minus C2. Right. So, now here problem 2015. This is a 14, now the 15. The cost of two independent process variable affects the total cost CT. Independent process variable costs are F1 or F2 as 100 F1 plus 1000 F1 F2 plus 20 F2 square plus 50. This is the cost function. The lowest total cost in lakhs of rupees into 1 decimal places. So what we have to do, del Ct del F1 is 100 minus this 1000 divided by F2 into F1 square, that much, and del Ct del F2 is minus 1000 divided by F1 into F2 square plus 60 F2, sorry 40 F2. Then that's equal to 0, this is equal to 0. So F1 F2 square is 1000 divided by 100 is 10. F1 square F2, and in the second case F1 F2 square is 1000 divided by 40, so 25. So if I take the ratio F1 by F2 or F2 by F1 is 25 divided by 10, so this is 5 by 2, right. And if we substitute here that F2 is 5 by 2 F1, so 5 by 2 F1 into F1 square equal to 10, so F1 cube is equal to 20 by 5 is equal to 4. Yeah. And here it is F2 square, so I have done a mistake here. F1 F2 cube, this is cube, is equal to 25. So if I divide then F1 divided by, or F2 cube or F2 square rather, if we take the ratio, F2 square is equal to this. So, we will not go by this equation, but rather it is F1 into F2 cube equal to 25. So, F1 is equal to 2 by 5 F2 square. So, 2 by 5 F2 square and cube, this is to the power 5, it is 25. So, from there F2 can be calculated and F1 can be calculated. We can check whether it is minimum or not by this positive definite matrix, Hessian matrix, that is form this D1, which is del square Ct del F1 square, or rather this is M1, we have studied it in maths. M2, it is del square Ct del F1 square, del square Ct del F1 del F2, del square Ct del F2 del F1, del square Ct del F2 square. So, di, we will calculate the matrix, determinant of that matrix. If all di are positive, then minima. So, you check this condition and from there you conclude about the minima. So, next is 2015 problem. A proposed chemical plant is estimated to have a fixed capital. Fixed charge or fixed capital is 25 crore. Assuming other costs be small, the total investment may be taken that working capital investment is 0. After commissioning, the annual profit before tax, annual profit before tax is 10 crore per year at the end of year. Expected life of the plant is 10 years. The tax rate 40% per year. Linear depreciation is allowed, linear depreciation. The salvage value is 0. If the annual interest rate I is equal to 12%, so 0.12, we have to calculate the net present value or worth. Right. So, this depreciation is 24 crore divided by 10 because the salvage value is 0. This is 2.4 crore per year. This is the depreciation. Right. So, tax is 40% of this profit. Definitely we have to subtract depreciation. So, the profit is 10 minus depreciation 2.5 crore. So, profit after tax is 10 minus tax. So, this will be 10 minus tax, that is the profit before tax, and the taxable, basically this is the taxable profit. Right. So, cash flow will be profit after tax plus depreciation. This cash flow we have to consider. And the depreciation has been calculated, taxable profit, cash flow. So, cash flow is taking place for 10 years. So, we know this net present worth will be F, or rather this profit into this, if this cash flow is CF, so CF into 1 plus I to the power n minus 1 divided by I into 1 plus I to the power n. This is the net present worth. That minus 24 crore F will be equal to your net present value. So, cash flow is to be calculated, profit after tax plus depreciation, and from there we should calculate the net present value. So, you see the net present value, we have to consider this depreciation and rather the cash flow, not the net profit. Right. So, there is another problem, like there are two options, option P and Q, and installed cost, it is given, installed cost in lakhs, it is 150 and 120, cooling water cost lakhs per year, 6, 8, steam cost lakhs per year 16, 20, right. The annualized fixed charge is 12% of installed cost. Based on the above number, what is the annual cost of the better option? So, you have to calculate the annual cost of both, right. So, here the annual cost will be 150 into 0.12 plus 6 plus 16, and here the annual cost is 120 into 0.12 plus 8 plus 20. So, whichever is lower will be my answer. Okay. The next problem. A vertical cylindrical tank with flat roof and bottom is constructed for storing 150 meter cube of ethylene glycol. The cost of material and fabrication for the tank wall, is 600. Tank wall is 6,000 per meter square, and the same for roof and the tank bottom. Roof bottom is 200. For roof it is 200. 2,000 and 4,000 meter square, rupees per meter square. The cost of accessories, piping, instrument may be taken as 100% of the cost of wall. Cost, accessory, instrument is same as cost of wall. 10% of the volume of the tank needs to be kept free for vapor. 10% free volume. What is the optimum diameter of the tank? D star is being asked. So volume will be 6,000, this 150 into 1.1, that is the volume of the tank. Let the diameter is D, height is H. So we can write pi by 4 D square into H is equal to 150 into 1.1. And next the total cost is pi dH, it is the wall, into 600 plus 2000 into pi by 4 D square plus 4000 into pi by 4 D square plus for accessories we have pi dH into 600, 6,000. So you see it is 12,000 pi dH plus 6,000 pi by 4 D square. Right. So this H is becoming 150 divided by pi by 4 D square. We go by direct substitution here, it is better instead of Lagrange multiplier. 1000 into pi d into 150 by pi by 4 D square plus 6,000 into pi by 4 D square. So D cancels out, pi cancels out, and we will have 4 here. So it is 12,000 into 4 into 150, that is a factor, into minus of 1 by D square plus 12,000 into pi by 4 into d equal to 0, and from there we can solve for this optimum diameter. উত্তম দা টাইমটা দেখুন হয়ে গেছে না বাকি আচ্ছা কেটে দিন So that's the problem of optimum diameter. So this is a very easy problem. I'm not solving it. See, the cost of a new pump, including installation, is 24,000. The pump has a useful life of 10 years. Its salvage value is 4,000 rupees. Assuming straight line depreciation, the book value of the pump at the end of 4th year. So V is equal to 24,000, N is equal to 10, and Vs is equal to 4,000. So the depreciable amount is 20,000, 24 minus 4, that is 20,000, and useful life is 4 years. So depreciation per year is 5,000. Sorry, 4 years. It's 10 years. So it is 20 divided by 10, 2,000. So at the end of 4th year, the depreciation is 8,000. So the cost will be 24,000 minus 8,000, which is 16,000. So that will be the answer. So additionally, another type of problem. The bond has a maturity value, I think. The bond has a maturity value of 20,000 rupees at the end of 4 years. The interest is compounded at a rate of 5% per year. The initial investment to be made. So 20,000 divided by 1 plus 0.05 whole to the power 4. So that will be the answer. Simply therefrom we can calculate the present worth. And another problem of 2017 is this equipment cost and two variable objective function is given. Ct equal to 2x plus 1,20,000 divided by xy plus y plus 5. So from there, taking the partial derivative, we can solve for this optima. So that's all for this session. We have solved some of the problems of project engineering. In the next session, we will go for these process calculations, and if time permits, some more problems on this project engineering will be solved. Okay, thank you. বন্ধ করে দিই।